Okay. Okay, so I want to thank the organizers for inviting me. It's my honor to be the last speaker. I hope to, and I thank you for staying that late and staying awake. Unfortunately, I have only one joke, and it would, and only the Americans and the Israelis will find it funny. You will soon see. Anyway, so I want to talk about demonstration of a passive photon-atom swap gate, namely quantum communication between material qubit and the photonic qubit. So let us think, what do we need in order to have, what is the minimum number of modes? What is the minimal system that allows communication between photonic and material qubits? So of course, if we want a photonic qubit, it means we need to send a single photon in one out of two modes. So we need two modes there. So two optical modes could be two polarizations, two frequencies, two directions. You know, it doesn't matter. A beam splitter could translate different polarizations to different directions and the other way around. So we just need two modes. So here we have two modes. So this is my photonic qubit, okay? Material qubit, the same. I need two modes, preferably two ground states. An excited state is not a good qubit. So 1, 2 photonic modes, 1, 2 ground states for the material qubit. Now, in order for them to communicate with each other, of course, we need some excited state. So that defines two more modes, right? This transition, but in order to keep the number of modes low, minimal, we can associate this transition, let's say, with this mode, and this transition with this mode. So we're still just with two optical modes and two ground states. Now, given that we have such a system, which indeed I think you can agree that it's the minimal system for communication between photonic and material qubits, what do we need to do in order to allow quantum communication? In order to make the photonic qubit and the material qubit swap their states. So that's the communication. So the surprising answer is nothing. And the joke is this. So, that's the last time I'm showing this joke. So typically it separates the Americans and the Europeans from the crowd. Yeah, so very much like, Seinfeld is a show about nothing. This configuration simply needs nothing to have the photonic qubit and the material qubit to swap their states. If you have this system, unavoidably, each time the photon meets the atom, they will swap their state. And you don't, willing or not. On the quantum emitter. The quantum emitter is, typically is a point source, or it needs to, So on this nothing, there are many theoretical proposals. So we're not even the first ones to think about it. So we thought we were the first ones in 2011. But of course, when we were writing this, we realized that Imamoglu stole our idea 3 years earlier. But we are the first to demonstrate experimentally. So let me show you first what is the principle. So let's begin with a field coming from one direction. So this is a single photon pulse. So it's a long pulse, longer than the cavity enhanced spontaneous emission time, longer than the response time of the system. And let's normalize the amplitude to be 1. Now, after some transition time, let's say that the atom was initiated here, that the system was initiated here. After some transition time, we will have steady state. It looks like this. We have probability amplitude for the system to be in one out of these three states. And it emits to both ways a field at the strength x. And x is equal to both directions because remember, this is typically a point source. So it doesn't know if the field derives from the left or the right. So now we have, assuming indeed that we have low losses, which is of course the challenging part. To have a lambda system coupled only to two modes of a waveguide is the challenging part. But assuming you have that, we can write the equation for the power, for energy conservation. So towards the right, we have 1 plus x squared. And towards the left, we have just x. So 1 plus x squared equals 1. So it's quadratic equations, two possible solutions, x equals 0, meaning do nothing, and x minus 1. So if x minus 1 is the steady state, it means that actually these two fields interfere destructively. So just by shining the probe, we have destructive interference between the lambda system and the probe, which means that this is a system that must reflect. Nothing can continue. Now, it shouldn't surprise us too much because this is also the mechanism of a mirror, right? A mirror, in a mirror, the field is coming in this direction. All the electrons in the metal oscillate and start radiating in both directions, and the radiation has a pi phase shift compared to the incoming probe, which means you have destructive interference in the forward and everything goes backward. That's a mirror. Also, that's how an antenna reflects light. If you disconnect an antenna, it's a perfect reflector. However, in this case, once we get reflection, the atom has to do single photon Raman interaction. So it's like a mirror, but it's a mirror only for the first photon. It's a mirror with a memory. After one click, after one reflection, the atom unavoidably switches to the right. And so, first of all, this is the highest possible single photon nonlinearity, because now if you send another photon, it goes through. So a system that was reflective became transmissive only after one photon. And you can also see that the atom determines where the photon goes. When the atom was here, the photon was reflected. When the atom is here, the photon is transmitted. You can see it goes also the other way around. The photon tells the atom where to go. If the photon came from here, the atom would end up here, either if it was there in the beginning, or because it scattered the photon and went there. And of course, everything is symmetric. If we want to do the other way around, we do this, and again. So you see, the atom and the photons play symmetric roles. One tells the other where to go, which means it's a swap gate if it works with a superposition. So assuming we send one photon in a superposition of modes, and the atom is initiated in another superposition of modes, after that interaction, what we get is that they simply switch their coefficients unavoidably if you have a clean system. So that's, of course, a swap gate. And if I can give another description, which may be easier, especially for NV people or quantum dots people and photonic bandgap people. And that's, so you could think of a Fabry-Perot. So why does a Fabry-Perot resonator transmits on resonance? Well, initially in the first nanoseconds, all the power, all the field is reflected from the first mirror. After a few nanoseconds or the cavity buildup time, you get radiation from this intracavity field, and that radiation is a pi phase shift. Well, it sounds familiar, right? Like, it sounds familiar because if you have only one photon, there's no difference between a linear system, a cavity, or an atom. They both behave the same. So because this system radiates equally to both directions with the pi phase shift, you cancel the backward reflection, and the only way out of this system is in transmission. So far, so good. So to do sprint, to do single photon Raman interaction, what we do is we simply replace this output channel with a 3-level system that leaks power back to another mode, to a different mode. And if you keep the collapsed golden coefficients of these transitions equal, you get, again, the same destructive interference, meaning that if you have a photon, let's say polarized H or a different frequency, then after the interaction, it bounces back in this frequency or this polarization, and the atom undergoes single photon Raman interaction. So, for example, put a quantum dot, a lambda over 4 from the end of a photonic bandgap waveguide, and you'll get this effect automatically. But you need a clean 3-level system. So I would just like to remind you what's the alternative. So a swap gate between photonic qubit and material qubit is not something that was, it's not a solved problem completely. It was performed mostly by Gerhard Rempe in MPQ. So they implemented the theory, the proposal by Dayan and Kimball, which is in some sense adaptation of the scheme that Serge Roche was using in microwave. So this is the theoretical proposal, and these are the experimental realizations, which are very, very nice, very high quality, very powerful. But they are complicated, and they're active. What does it mean active? You need control fields. For example, to map a photonic state of a photon into the atom, what do you need to do? So first, this stage means you need to prepare the atom in a superposition state. That means shining classical high-power laser beams on the atom or microwave fields, preparing it in the superposition state. So that's one control field. Then you bring the photon. Then you shine again pi/2 rotation. You shine again Raman beams on the atom to rotate its state. Then you shine again laser fields to measure the state. Conditioned upon the result of this measurement, you may or may not rotate the state of the atom again. So 1, 2, 3.5 times, we need to turn on high-power laser beams or Raman or microwave beams to control the state of the atom. And the other way around when we want to map the photon out. To map the state of the atom to a photon, we scatter the photon, that's this interaction, and then we rotate the state of the atom by Raman beams, measure the state of the atoms by laser beams, and then, conditioned upon this measurement, may or may not rotate the state of the photon. So it needs to stay. So when Gerhard Rempe demonstrated this part of the protocol, they had the photon waiting in a 3-kilometer delay line for the result of this measurement. So this is a very powerful scheme, the Dayan and Kimball scheme. However, the fact that it's active means that it's A, complicated, and B, also long in time, slow. So in this case, the interaction happens automatically on the cavity enhanced spontaneous emission time, which is nanoseconds. So it's deterministic, it's passive, which means it's scalable. So, you know, we have digital circuits with billions of transistors. Why are digital circuits are so scalable? Because they're passive. You don't need to tell one transistor, please wait, we're preparing you to get the signal from your neighboring transistor. We just send the voltage pulses, and they propagate through a passive system. So this is the advantage of this scheme. Do nothing scheme. Just send the photons, and everything is already, all the wisdom, all the interactions are programmed into just the connections. And so you could imagine how this can scale up better. And also, it should work with any lambda system, as long as it's a clean lambda system coupled to 2 modes of a waveguide. And once again, these are all the theoretical proposals. And here are for the experimental realization. So, so we have a vacuum chamber here. Inside the vacuum chamber, we have these microsphere or microtoroid resonators invented by Kerry Bahar's group in Caltech. But we manufacture them at the Weizmann Institute. So they lie inside here in this vacuum chamber. And all the system is connected to the bottom flange of the UHV chamber. So when we want to change the resonator, it's painful. It takes a day, but it's something that usually is not done in cavity QED systems that we open on every few months. So we just open the bottom flange and take everything down, replace, for example, the chip or the fiber, and put it back in. And we don't trap the atoms yet. Trapping close to whispering gallery resonator is yet to be achieved. So people like Arno, Julien, and Jeff Kimball by now have trapped around the fiber. Trapping around a whispering gallery mode resonator was not done yet. We may attempt it now, but so far what we do is we just let the atoms fall, and then we have a few milliseconds in which the atoms rain upon the chip. and we simply detect the presence of the atom in the evanescent field before and after, and then we know that we can take this experiment as a valid experiment. So 2 clicks here, 2 clicks there means that we can consider the result of this experiment here. So the way we make a lambda system, we use TM mode, and as I guess many of you know, the polarization in the evanescent field of a TM mode is actually circular. So it's a funny circular because we're used to helix-like circular polarization. But if you shine horizontal polarization into a nanofiber, then at the evanescent field, let's say on the right side of the fiber, you get this frisbee-like, or Arnaud says helicopter-like polarization, which moves like this, forward, and in the other direction, it's the other way around. Well, you will actually see such polarization also at the focus of a tightly focused Gaussian beam. To focus something tightly, you need these non-longitudinal, non-transverse, yeah. Yes, longitudinal, yeah. So this has been known, I guess, for a long time, but the first one to point at the use of this effect in the cavity QD was Arnaud Rauschenbeutel, and I will refer you to this nice review about chiral quantum optics if you want to read more about this effect. So to make a long story short, if you send photon from the left, it's mostly sigma plus. How mostly? 95. If you send light from the right, it's mostly sigma minus. How mostly? 95%. So the first experimentation we did was 3 years ago, and we demonstrated, in some sense, the classical operation of this swap gate, meaning we sent light only from the left or only from the right. So and depending upon the state, the direction we sent the first photon, the second photon would either reflect or transmit. And we have 90% transmission when we want it to transmit 100%. It sounds high, but actually we try to do nothing and fail. So why 10%? Most of it is because of polarization. We have 5% preparation error, because sigma plus is not sigma plus, and 5% reflection when we don't want to, because sigma minus is not sigma minus completely. So this explains this. On the other side of the coin, we have just 65% when we want it to reflect 100%. Why 65? We believe we know all the imperfections. 10% out of this is the imperfect polarization. Another almost 10 is the fact that it's not a single lambda system, but there are other levels. And almost 7 or 8% more is because the atom doesn't fall at the same place, so we have a varying cooperativity. Okay, so but this in a sense is just a switch. A photon comes from the right or the left and tells the atom to be in one state or the other, and thereby reflecting or transmitting the next photon. The next experiment we did was to increase gradually more and more and more photons in the pulse, and show that indeed we grab the first one and let all the others go. So it's extraction of a single photon from a pulse, and to differentiate this from subtraction, because so indeed we subtract one photon from the ongoing field, and we do that deterministically, not like with a very weak beam splitter. And also, in contrast to a beam splitter, we keep that photon. We can do whatever we want. We don't herald the result of the success of the subtraction on a click. So deterministic extraction of a single photon. So what you see here, in the absence of the atom, the transmission is just linear, and there's no reflection. When we have an atom, then the reflection saturates almost completely towards 1, and the transmission goes to n minus 1. We still have a gradual increase here, which is exactly the 90% instead of 100% transmission because of the imperfect polarization. So eventually, when we have 100 photons, we will have more than one photon going through. But even up to 11 photons, it's still roughly 1. And these are the statistics of the reflected pulse. And you see they're sub-Poissonian. G2 of the number of photons at the same pulse is measured 0, expected a little bit more, but it stays below 0.5 up to 10 photons. So it's indeed a single photon. And this is the distribution of the forward-going light, which is just Poissonian shifted to the left. Shifted one to the left. And the last experiment we did, actually last summer, was to demonstrate swapping in of all 6 possible states on the Bloch sphere and swapping out again. So this is the experimental setup. So to prepare or to send and read pole states, just North Pole or South Pole, we send light only from this direction or only from this direction. However, when we want to send and read equator states, like these, we send them through a beam splitter. By adding a phase, we can write X or Y axes on states on the Bloch sphere. And however, when we want to read, so that's for the writing, when we want to read, we always read from here by sending light from there. We have injection port here because, of course, we're not allowed to change the way we read according to what we wrote. That would be cheating. So, and the right pulse has average, is Poissonian. It's a laser. So the right pulse has an average of 0.8 photons. So bear in mind that 0.8 photons, meaning in 40% of the cases we have vacuum, 30% or so we have one, and almost 30% two. So yes, sometimes we don't write anything, and sometimes we even write 2 of them. On the read pulse, we kept the power even lower, 0.05 photons, to keep the probability of a second photon much, much smaller. Now, why do we try harder here than here? Because if we wrote twice here, well, that's good for us. You know, we could later compensate for that or take that into account. So in some sense, if there are 2 photons here, it doesn't hurt me. It hurts maybe the reviewers of the paper. But it's good. But here, if there are accidentally 2 photons on the read pulse, then in half of the cases I will detect the second, which means that I read nonsense because I will read just north. I will read the state set by the previous read photons. So here we kept the number of photons very, very low. So we had a very low data rate as a result. So here are the results. So the first thing we did was just to prepare along some axis and then read along that axis, which is just measuring sprint. So when we do that along the poles, it's just repeating the experiment, the regular experiment we did previously. But then we do it also along the equator through the beam splitter. And we have roughly the same result in all axes, which is average of 85 when we want to transmit, and average of 65 when we want to reflect. Bear in mind that that includes preparation errors, so we can add 5 to both of these roughly. But what we measured is 85 and 65 on average. So sprint indeed is coherent. It doesn't care if we send it through a beam splitter and then there's a standing wave on the whispering gallery mode, or if we send it from one end or the other of the fiber, which means we have a traveling wave in the whispering gallery mode. And now for the full swap state. So first we want to take a material qubit and map out a photon in order to do some communication. So here we prepare the atom as best we can, typically by roughly 1 photon. And then we send another photon from always from the North Pole to read it. And this is the average fidelity of all the 6 possible inputs. We write larger than 72.4 because it includes preparation errors. So without preparation errors, it should be closer to 77. And note that the classical threshold should be 2/3. Why 2/3? Because a classical measurement would have to guess along which axis we sent the qubit. So if we accidentally guessed right, then we would be right 100%. If we accidentally guessed wrong, then we will read nonsense, meaning 50-50. So the average of 100%, 50-50 twice is 2/3. So This is higher than 2/3 the readout. Now, the next thing we would like to do is to measure the other way around, to send a Fock state, and then measure the atom and see how good it was. But actually, it's not something we can easily do. A, we don't have a Fock state. We have Poissonian statistics. B, we can't read the atom perfectly. The way to read is send another photon. So why? Because the atom is not trapped. So we don't have all the time in the world to send classical fields and do tomography, unfortunately. That would be desirable, but this is not what we do. So the experiment that we did was actually a double swap. We send a photon in, and then immediately, a third of a microsecond later, a photon out, and we analyze these results, and following these results, we can infer what we have in the right procedure. So these are the results of the double swap. So we have two sets of results. One of them is unheralded, meaning we don't even check if there was a photon in the right pulse. So in 40% of the cases, we actually didn't write anything. This is why it's, and then we read again. So these are, so the level here, the threshold here, we can discuss what is the classical threshold for this state. Could be either 2/3 if you consider it as a single operation, but actually it's two operations between 2 qubits. So it's actually more like 5/9. And anyway, but when we herald on the preparation on the right photon, meaning we check that the right photon survived and was not lost on the way, we get 64. Why it's such a low difference between the two? Because remember that if we send nothing, we don't go to 0. We go to 50-50. So based upon these results, we can, and these measurements, we extract what is the most probable photon-atom right swap fidelity, which, as expected, it's very similar to the atom-photon. So the photon-atom is very similar to the atom-photon. It's 74, and these are already values for a single photon. So it's 74 if we herald on the survival of a right photon, and 70 if we don't. Okay. So, and by the way, these are roughly the results. So this was not submitted yet. Oh, it's been a year. Yeah, I guess I'm not the only one here that have these problems. But the theoretical analysis has been published already, and it's very similar to what we expect. So we think we know all the imperfections. So let me summarize. Sprint is a passive mechanism. Just put a 3-level system in a single-sided cavity, and it happens. And it's not only simple, it's also versatile, because it's not only a swap gate. So take this proposal by Kazuki Koshino and Nakamura. You can actually, if you just detune the fields, so you reduce the probability of your swap to 50%, which actually means you have a square root of swap gate. Maybe I swapped, maybe I didn't, which is universal quantum gate. And Koshino and Inomatai also have another proposal in which just by adding linear optics around this, around the 3-level system, you can get a controlled phase gate. So based on the similar building block, you can do universal quantum gates, which are more interesting, than just a swap. A swap is the identity. So you can have square root of swap or controlled phase. You can write in one wavelength and read in another. You could do photon number splittings on quantum key distribution. So Alice wants to send Bob single photons. Accidentally, sometimes there are 2 photons in the pulse or more. So if it's only 1 photon, then the first photon reflects from here, and goes to Bob unharmed. If there's another photon or more photons, then they are transmitted here. One of them is reflected to Eve, and the rest continue to Bob. So just by concatenating 2 systems, you always steal the second photon. So stealing 1 photon only if there's more than 1. This is a scheme which I like very much. Look, you send a superposition of these 2 states, of these transitions. You prepare the plus sign here, state. Then you scatter a photon, or then you scatter your pulse from this cycling transition. So, and if you had nothing in the pulse, then the phase of this superposition would not change. If you have something, If you have one photon, it would change to a minus. And then when you read again the state of the plus or minus here, you know if there was a photon or not. So that's a quantum non-demolition measurement. And actually, if you consider what happens with larger Poissonian numbers, a Poissonian distribution, so actually if you send a Poissonian state here, then this system is basically parity measurement, right? Based upon how many photons were scattered here, we will get a plus or a minus here. So when we measure this, we will project the reflected pulse to a cat state, a perfect cat state, not like in down conversion, which is a thermal mixture of plus and minus, of even or odd. In this case, it's Poissonian combination of plus or minus, of even or odd. And lastly, a quantum repeater. So, but this time deterministic, based on a single emitter. So you prepare both systems in the reflective state, send one photon through a beam splitter. If you get a click here, you know you prepare the plus untangled state. If you get a click here, you know you prepare the minus. So very much like the DLCZ, only deterministic with single photon. And last thing, I would like to point at the works of Inomata, Koshino, Nakamura, and Yamamoto. They have, shortly after us, they had demonstrated this in microwave. So they call it something completely different. Down conversion with impedance smash lambda system. If we didn't spot Kazuki Koshino in the authors list, we would never notice that it's the same thing. But it's the same thing. It's a lambda system, which is something very hard to do in superconductors. And by now they have another work in which they use it for single photon detection, single microwave photon detection. So they send a microwave field, it flips the state of the superconducting qubit if there's one photon there, and then they read the state of the superconducting qubit and know if they had a photon or not, achieving, I think, roughly 65%, which is what we get in optics for a single photon detection, but in microwave. And this is the system that is typically used, for example, in Rainer Blatt's setup or Tracy Northup. So calcium-40 is what is used for quantum information processing, and you can identify very convenient lambda systems there. And we have a theoretical scheme that we write together with Tracy. It can be implemented even in this seemingly complicated level structure. So this is a very, very versatile and useful and powerful, I think, building block. And this is it. Okay, thank you very much.